All right. So the claim was this is the effective theory for the Laughlin state, and we know now a lot of properties of the Laughlin state. We derived them. Here we've seen that the field interaction is correct.
Coming in there. Okay, come back. Not to be in the way for that chair, so terrible. Sorry.
But we computed a bunch of other things. We computed that the excitations, which are quasi-holes, have fractional charge and fractional statistics. Very striking. And that was quite a hard calculation, if you remember. That was really the longest calculation we did in these lectures, figuring out the Berry phase and using the plasma analogy. The other calculation that we did was topological order. We showed that if you put the Laughlin state on a torus, it has a degenerate set of ground states of some particular number. So we'd like just to see how all of these properties emerge from this effective Chern-Simons. So that's what we're going to do in the next 15, 20 minutes or so. All right, so quasi-particles. When we discussed Laughlin wave functions, I made this distinction between quasi-holes and quasi-particles, one being the antiparticle of the other. Here, by quasi-particles, I'm just going to mean either the quasi-particles or the quasi-particles. So, how do these arise? The current that couples to capital A is by definition the electrons. But now we've got a new gauge field, little a, and the things that gauge fields want to couple to is currents of their own. So we could ask, what are the objects that are charged under the loop? So we'll couple little a mu to a current of its own, which means that we'll add to the action below this. Okay. And the only thing we'll insist is that d mu j mu equals. Okay. So what do I mean by this? You could implement this in two different ways. You could either just put in a background fixed current. For example, you could put in a choice of delta function for j mu that's sitting at some particular point in space and persists in time. Okay, that would just be inserting a background charge into this theory. Alternatively, we could just add a whole new sector to the theory, maybe a scalar field. Scalar field which couples to a mu through the usual current interaction. In which case, this is going to describe dynamical quasi-holes and particles that can exist in the theory. And we can give that scalar field any dispersion relation we like, down to the state parameters. We have all of this stuff. So we have the choice either just to put in fixed background objects, or to allow this to be a theory of dynamical objects which can move around. Depending on which question you want to ask, both are useful. In this context, I think I'm just going to put in fixed background charges and just see what their physics is. Okay, so let's see what happens. Let's set a mu equals to 0 now. Which is allowed because, unlike little a, capital A is just a background field which is under our control, and I can do whatever I like. So I'm just going to do this. Okay, but the equation of motion for little a mu is e squared over 2 pi h bar f mu 1 over m x1 mu rho j rho. So if I put in a static charge, so what does this mean? I'm going to say ji equals to 0, I equals 1, 2. So this is just placing a static object at the origin, coupled to little a. It has charge E. That was actually an assumption from the previous lecture.
So this small a mu has only the Chern-Simons term in its section?
Yes.
No a mu
Do you know that in general there could be plus dot dot dots in this effective action. Those dot dot dots could include a whole slew of terms, all of them gauge invariant, and the first important one would be the maximal term for little a. This would affect this, but if you look at the solution of long distances, then the f mu nu squared becomes literally irrelevant because it's got two derivatives. So you can have as many terms as you like here, but if we talk about long distances, this is the only thing. Okay, so this is just a static charge, and what we learn is that if you put in a charge in this system, it carries with it a little magnetic flux, and the magnetic flux is the right normalization is, we should probably be setting h power e to 1 by that. Every other book has that, you idiot. But the flux is flux of 1 over n. Meanwhile, if you look at the electric current, that's capital J, that's the current of electrons, the current that couples to electric charge is the better way of saying it. That's given, it was given by the thing up there, it's given by the epsilons.
The flux 1 would turn these into fermions? I mean, would give you a minus sign on the interchange?
I think that's true. Let me actually write down the formula, which we'll get to in a moment. That's true. 2 units of flux keeps the statistics the same.
Right.
Well, that's true if these are bosons.
Yes, yes.
Okay, so this is the electric charge, the genuine electric charge in the system. And something that carries charge 1 under little a, if you go through, carries charge 1 over m, and generally e over m, under capital. Okay, so this is the electric charge. E over m, which is exactly the electric charge that we had for a quasi-particle. Particle depending on the minus.
Something which has little charge with respect to little a has charge e over m compared to the external.
That's right. Charge 1 with respect to little a means charge 1 over m with respect to the genuine electric. Which is, of course, exactly what we wanted. Exactly what we saw using Lofty examples. Okay, meanwhile, let's do fractional statistics. And, we had a bit of a discussion before about fractional statistics and fluxes going around other things. And there's a subtle factor of 2. So here I'm just going to try and spell out that factor of 2 on the board. And we'll do the cheap argument, and they'll all complain because it looks like there's a factor of 2 missing, and then we'll do the correct argument because the cheap argument was actually right. Okay, so for fractional statistics, so each particle, I should say each quasi-particle, has charge equals E. This is all under little a. Little a nu is the dynamical degree of freedom that will respond if you put these charges in. And flux. So capital phi is a flux. It's going to be the integral of f12 over the plane. Pi h bar all right, so when we thought about wave functions, we had this sort of Jane picture, really it's sort of more due to the big read as much as Jane, where you have a quasi-pole and you think about vortices attached to quasi-poles, where vortices attached to electrons or quasi-poles, where vortices is really where the phase of the wave function points. And then we were thinking about moving these objects around each other. Here, it's a little more physical. So there's no wave functions, but what you have is that every time there's a charge, little e, it comes with a magnetic flux. And so now the story is the Aronoff bonus story. that you have one particle here, another particle here. This particle moves around this one because it's going to pick up an Aharonov-Bohm phase because it's encircling the flux. So there's an Aharonov-Bohm phase. And the Aharonov-Bohm phase is e to the I q of the particle phi divided by 2 h bar. So this 2 is an uncontroversial 2, and then I'll tell you about the controversial 2. So this 2 is because the Aharonov-Bohm phase is usually a particle moves all the way around the flux and picks up phase e to the I q phi over h bar. But it exchanges with that. Exchanges only moving halfway around the flux, so that's that factor.
So the factor of going all around with 1 unit of flux is 1.
Where 1 unit of flux means no m there, that's right, yes. For exchange, rather than. What's a word for going all the way around? Rather than 2 pi rotation. Rotation's not quite right, is it? 2 pi circulation. Okay, so this is e to the I pi alpha, and alpha is 1 over m, is the statistics.
And just to make sure I'm getting the connection with the previous picture, right?
Yeah.
Particles with charge 1 under this new gauge field are the quasi-particles of the Laughlin state, and a bound state of m of these quasi-particles will be an actual electron.
Did he say that? I mean, the charge is right, but is it actually true?
Yeah, we saw that in the Laughlin picture,
Yeah.
explicitly. That is to get the electron wave function.
Oh, I see. There's something over there.
Okay, so this is the statement. You have a particle of charge q, another particle, 2 particles the same, basically. This one goes around this one, but this has charge q, this has a flux phi, so you pick up this Aharonov-Bohm phase. Okay. Why is it a dodgy argument? It's a dodgy argument because this particle also had flux phi, and this one also had charge q. So you might think, you missed something, because you pick up the phase as q goes around phi, but you also pick up a phase as phi goes around q. So there should be another factor of 2 here. That would give the wrong answer. Okay. So why is this the right thing to do and not the thing that seems to be the right thing to do? And I'd love just to give you a sleek reason why this is the right thing to do. Just give you a one-line answer. There probably is a one-line answer, but I don't know it. So the only thing I know how to do is to do the calculation. The calculation is only a few lines, so I'm just going to do it on board. We'll see that this is the right answer. Maybe if I do the calculation, then we can try and figure out the one-line answers. There's a bunch of papers, but none of them really have any compelling reason why this is the right thing to do. Okay, so what's the calculation done better? Okay, so what we're going to do is just set up a bunch of particles, and we're actually going to think about the physical situation. So the particles will put in some position, but then we'll also move them around each other. Okay, so there'll be fixed charges under our control, but now charges that are encircling each other. So we'll consider n particles, and the currents will be J0 is E, 1 to n, x minus xi of t. So these xi's are the positions of the particles which now move, and the spatial parts of the currents will be E, 1 to n, x dot I minus t. Okay. On this board earlier, I wrote down the equation of motion. It was basically F12 equals, well, mj0, but then there's the other parts as well. So you can just solve the equation of motion with these currents on the right hand side. The equation of motion for the Chern-Simons gauge. So solve equation of motion for A mu. Useful to pick a gauge, and the gauge we'll pick is A0 equals 0. DI, AI is 0. And the solution, easy to check. Two things collide. How annoying. Which one can I look for these? Good. So alpha is the station index point. So epsilon of beta x, beta minus x point I t divided by the mod x minus x I t squared. All right. So you can just check this is the thing which solves the equation of motion, Chern-Simons equation of motion in this chosen image.
The complex coordinates that would be kz is zi minus 1 over zi minus zj.
Yes, in fact, what is what? If you remember when we did the Loftin wave function calculation, we spent a long time using the Plateau analogy, and then we computed a Berry phase. That's exactly the same as this. The Berry phase from the Loftin wave function is this term. And there it was written in complex coordinates, so I can just tell you the answer, and it's 1 over zi. Sorry, 1 over z minus z. Okay, so that's the solution. And the phase change. So what do? We're going to take one of these particles and move it in some trajectory that's going to encircle some number of paths. So let's just take the first one and move it on a path and encircle just say 1. So the phase change now comes purely from this gauge field A. The phase change is the exponential of IE A dot x1, where you move in some path.
What makes this really simple is that it's instantaneous.
Exactly, yeah, because there's nothing propagating, right? Yeah. There's no waves traveling down, radiations.
Positions at that time determine the gauge field at that time.
In this gauge, yes. So this is the answer. Do the calculation. In fact, we already did the calculation because it's exactly the same as the Berry phase calculation we did 4 weeks ago. So you do the calculation. As you find the statistics is again. Okay, so this is the way to do it properly. Like I said, I'd love just to have the one-line reason why it seemed to be wrong before is actually correct. Why you don't do this double counting of charges and fluxes.
But just to say again, suppose we're just doing this perturbatively, you'll be summing Feynman diagrams.
Okay.
The first Feynman diagram is a tree-level exchange of the photon.
Yeah.
Okay? And that tree-level exchange can be thought of classically as the second particle moving in the field of the first.
Yes.
So that shows that there's no factor of 2. Because it's just the second particle moving in the field of the first. Field of the first produces.
Yeah, the thing about that argument, which is the argument we had given last time.
Yes.
The reason I got a little worried about that argument here is that the second particle will move in the field of the first, but this second particle has both a charge and a magnetic flux, right?
Yeah.
Right.
That's why I'm a little worried because
Yeah, I could have counted 4, right? I could have said I undercounted by 4. I think this is what you're saying.
Yeah.
This charge moves around this flux, and this flux moves around this charge, but this charge is,
And then Shiraz's argument, I think, is right for 1 factor of 2 out of that 4, I think, okay? But in my mind, I still got a little worried about 1 factor of 2. That's why I held back. But maybe I'm wrong, but you know, that's...
The first particle, suppose the first particle is at rest, it produces a uniform magnetic field. And then the second particle moves. In the background of the first, it's moving in a magnetic field. In the gauge field, you do a magnetic field. That has a magnetic field, makes no difference.
I think, okay, then if we don't allow, if we have the first particle only giving rise to one or the other, then I think you're right. Maybe we do that. We get rid of that factor of 2 by
there's no electric field because there's no the Maxwell. This is a charged particle coupled to Chern-Simons. So the only effect it has is producing the magnetic. Something goes by that will also produce an electric. But that doesn't
you're saying just hold it static.
Yeah.
Okay, if you hold it static, then I'm happy. Yeah.
And then actually, if you just move the center of mass.
If more change, then you get extra contributions from this calculation. So if more things are moving, you get extra contributions.
So this, because here you allowed all the n to move. So then
I did, although ultimately I just
moved one perhaps.
No, suppose they were all moving, but ultimately just one encircled the others. The others may be moving.
Yeah.
I think this is still the answer.
Yeah, I think it's always the answer. For instance, if the moving doesn't matter, you can go to the center of mass coordinates. And that would be an effective motion of a particle in this unit.
Okay. Yeah, in any case, we can calculate it by holding one fixed.
Yeah. If you do that, it's clear.
Then it's clear from last time also.
Yeah.
And then, okay. Alright. Okay, but anyway, okay. It's nice.
It still strikes me as odd. There's no. Firstly, this is obviously a field theoretic calculation. There's still some kind of just. Before we were just trying to think of quantum mechanics, right? Just particle.
It's not really field theoretic, right? Because their source is basically it's classical.
Classical, but it's classical field.
Okay, I see. Okay. Can I ask one question, which is, and we can come back to it later if from the class, but so at the end, this is perhaps why what you're giving so beautifully in the last lecture, and this one is, in the end, why everything works. You have all the dirt, you have everything, and still E is the most precisely measured quantity anywhere in the universe through the Hall effect, and it's probably because, in the end, it's Chern-Simons theory. But maybe go back to something that Shirag asked last time. Is there, to get a slightly more satisfactory feel for it, is it practical to take the Laughlin wave function for the fractional quantum Hall effect and in some way try to derive this effective theory out of it?
Good. So there's a few things to say. Where we're going is to start with this and derive the Laughlin wave function. We're actually going to go the other way. That's going to be via Edgeworth's. So we'll get back. To go the way you want.
The reason why I hesitated, I don't really know how to. I could think of deriving the capital A terms because that's an external field I would couple to the electron.
They can sort of derive this. In fact, the place people first stumbled upon Chern-Simons, the condensed matter people, was by trying to derive this starting from the Laughlin wave. I think it's wrong. So I wasn't going to cover it in this lecture, but I can tell you briefly now how it works. So what they wanted was to write down some kind of Landau-Ginzburg theory for the Bohr states. And so the first thing you need is some kind of order parameter. So what's the order parameter that you come up with? Because there's nothing obvious. There's no obvious symmetry in the group. So they wrote down some kind of off-diagonal long-range. Do you know what this is? I don't even know what this is. So it's something which appears in superconductivity. So you write down what's called a density matrix, which doesn't mean what you think it means. So it's not the same kind of density matrix as in, say, quantum information. You take the wave function of interest, you focus on one of the components, and then you integrate over all the others. Okay, so you get some sort of correlation function between. In the theory of superfluidity, you're in the superfluid phase. Precisely.
One of them is R and R prime.
One is R prime. Sorry, thank you. Yes. You're in the superfluid phase precisely if this tends towards a constant. R minus R. So it's some kind of order parameter area inside. So the idea was, see if I can get this right. Maybe there's some kind of hidden off-diagonal long-range order in the Laughlin states. So you can compute this in the Laughlin states. You find it doesn't tend towards a constant. Decays off very quickly. So then there was some long story about trying to gauge transform, I think gauge transformations to the Laughlin states in such a way that you added very singular gauge transformations, which were basically trying to do what this flux attachment here is doing. And slowly people realized that you could get something that looks a little bit like off-diagonal long-range order, but only with this very singular gauge transformation. And then they realized this very singular gauge transformation was related to Chern-Simons terms. And so they kind of went from there to write down an effective theory for Laughlin states. But the effective field theory they wrote down is the following. So this was the original effective field theory. It's by Zhang, Hansen, and Kimmelson. And it's the theory that most people talk about with Chern-Simons terms in the fourth form. And it's the following. So it's HK. Yes. There's some dynamical field, I, which is supposedly the electron field. But an electron field having done some weird singular gauge transformation. There's non-relativistic kinetic terms for the electron field, and then I screwed it up already. We couple this to this background gauge field.
This is your capital A, right?
This is little a.
This is little a, okay.
We can turn on capital A as well.
Okay.
And then you have the following Chern-Simons. With a 1 over k, so I should do this in notation. With a 1 over m, not an m. So everything we've been discussing about the topology and the quantitative, that goes out the window in this theory. But if you compute in this theory, you'll find that it gives the same. I'm going to call these tildes actually, just so because they're not quite the same objects. They're emergent fields, but different. So this is the theory that most people discuss in the literature for the effective field theory of the Chern-Simons. But you can see it's wrong, right? There's nothing that fixes this to be. You just have to tune this by hand, and
it's even not right.
And it's not allowed. It's illegal to do this. So what's the story here? So I think it is something which has now been understood. There's a particle vortex duality, 2 + 1 dimensions, and it maps bosons, free bosons to bosons coupled to gauge fields. Okay, the vortex is in one because the particles in the other. It's mirror symmetry. Supersymmetric language. If you take that particle vortex duality and you couple it to a Chern-Simons term, then there's a duality between the theory we've been writing down and this kind of theory very soon. But the duality only works if you integrate out certain gauge fields, which is illegal, to generate this kind of one. So it is understood what the relationship is between them now. It's in the literature. It's fairly easy to draw the relationship.
Sorry, thanks, and you should go on. But even here, the question would be, what is little a? Right? There is if I were Laughlin, I'd just give a wave function to you, and then it would be nice if you could say, okay, the reason why Laughlin worked is in the end it gave rise at long distances to this effective field here. Except you need to have some way of understanding what little a is in terms of the variables Laughlin used. And
here is some weird singular gauge.
I asked this because you said about the berry phase coming out right. That sort of suggests that, okay, we try to write the Loftian wave function in terms of the berry phase and the other stuff. The other stuff is heavier degrees of freedom. The long distances, all you care about is the berry phase part of the wave function. Then you integrate, something like that. I mean, that's why I asked the question. But, okay.
Yeah.
Right, and then this whole idea you had about universality classes of wave functions, you could translate into universality classes for field theories, like that. I mean, anyway,
which is much cleaner. Yeah, maybe there's, because it's obviously what it's doing. It's implementing that very phase. So just to summarize this diversion for everybody, there are two effective field theories in the literature. The correct one was developed by Wen and Z in the 90s, and it's the one we've been doing. Where correct means if you care about mathematical niceties like quantizations and Chern-Simons things. And the correct one has the electrons appearing as vortices, by which I mean the electrons are the flux of little a, and the quasi-particles being the things that are electrically coupled to little a. Okay. Then there's an alternative one that's in there, where those two statements get reversed. In the alternative one, the electrons are the things which couple directly to little a, while the vortices of this theory are the quasi-particles. This new theory, which is particles vortex dual, is missing important topological features. And this was actually the first way that Chern-Simons approached. I describe all of this in great detail in the chapter in the notes, but I decided I would go back to it. And there's been lots of interesting developments recently about how to apply this to the half-filled Landau level, and a new idea of duality that Song discovered, that Ashvin told us about back in January. Okay, other questions? So the next thing I want to do is...
are you going to give these quasi-particles dynamics and so on?
Yeah, I absolutely could if I wanted to. And there's questions where that's interesting. I'm not going to do any of these things.
So, for instance, we want to understand transport at finite temperature, one of these quasi-particle states. You will have to know how these quasi-particles propagate.
I think that this dual picture, even though it's incorrect, it's probably better for understanding those kind of, at least I'm told it's better for understanding those kind of questions. Because the electrons are the fundamental.
But it's not like the quasi-particles actually the genuine fundamental degree field that are moving around.
So there's an experimental question here, which is can you take these wall states, which might be a little precarious, and heat them up to such a point where the temperature is bigger than the gap for the quasi-particles, and these things are really now active dynamical degrees of freedom, without destroying the wall state?
Yes.
I don't know what the answer is.
Okay.
I've certainly not seen any literature that discusses this. That could easily be. Okay, so I want to look at one last thing, which is important, which is this idea of topological order.
So just come back to that. Suppose we take the limit where the first Landau level is much lower than omega. Mm-hmm. So B goes to infinity. We can take that limit while holding the quasi-particle gap fixed.
I think that's right, yeah.
And then if you heat up the temperature, order the quasi-particle, how could it be destabilized?
That sounds... No. This is fractional quantum effect. The gap is not set by B. It's not the Siemens bit, it's the Coulomb.
The gap between... Right, good. This is the gap for the quasi-particles, right?
No. So these are Landau levels. This is B.
Right.
Okay, but now you turn on interactions.
Right.
These get smeared out. And there's some little gap between the third filling and U equals a third. There's a gap between U equals a third and U a bit more. And that gap is split by the set by the Coulomb.
I see. And you said that gap might be the same as the quasi-particle.
I don't know if it is or not. I don't know what else is in the game per se.
Sure. Your questions were whether you could have additional matter coupling to the Chern-Simons theories.
Yeah. I mean, the quasi-particles should propagate around, so then it will be a matter Chern-Simons theory with the quasi-particles. And I was wondering whether the dynamics of that matter Chern-Simons theory was ever important.
Okay, so if you remember what topological order is, you take a Lofton state, you put it on a torus, it has some number of degenerate ground states. Well, we argue this is just a very general ground that that has to be communicated. It'd be nice just to see how that emerges from the Chern-Simons theory, and it's very easy. So let's consider the Chern-Simons theory. Torus T2. Here's the torus, and there's two cycles. We're going to call a curve which wraps around this circle, gamma 1, and a curve which wraps around this cycle, gamma 2. And the Chern-Simons action this is the Chern-Simons action. I'll turn capital A off because I've been out to turn capital A. Okay, so we just care about this. And the equation of motion is F mu equals 0. In fact, let me work in A0 equals 0 again, in which case the equation of motion is F. So this looks totally trivial. And even though it looks trivial, it has a very rich set of solutions. One of the things I may do later in this lecture, although we'll see how we go over time, I may not, is talk about non-abelian Chern-Simons things. So in non-abelian Chern-Simons, this has an amazingly rich set of solutions, which takes a lot of work to just try and count how many solutions there are. Here it's much easier, so I'm just going to find all the solutions and then quantize them. So it's probably worth first saying, actually let me first find the solutions, then I'll talk about quantization. So this has interesting solutions. And I'm actually going to leave this. I'm going to call the torus S1 times S1. And I'm just going to give names to the periodicities. So Ri of the periodicity is a radii of the two circles of the torus. Okay, R1 is the radii of gamma 1, and R2 is the radius of gamma 2. Okay, so what are the solutions? The solutions are the Wilson lines. Well, let me tell you firstly how you think of the solutions. The solutions are just A1 is constant around here, and A2 is constant around here. Now, specifying A1 and A2 is not a gauge invariant statement. So rather than specifying A1, I'm going to try and write down a gauge invariant object that captures this information. The gauge invariant object is the Wilson line. We'll see that this Wilson line, as I'm about to write down, also is not quite gauge invariant, and I'm going to have to work a little harder to make that gauge invariant. So the Wilson line Wi, maybe the Wilson line is supposed to be exponent, but I'm going to call, sorry, this is going to be little Wi. So it's just the integral of the gauge field around one of these two sides. Now, this looks gauge invariant because little a under gauge transformations changes by a total derivative. And it looks as if you're fine because you've done the integral. But remember that when you're on a circle, we're allowed these large gauge transformations that one. And these large gauge transformations basically shift a to a plus at least the 0 root of a. And this isn't invariant. This is not. invariant under large gauge conditions. So these are the things we discussed in the last lecture. Which shift Aj goes to Aj plus H bar. In the last lecture, the shift was 1 over beta because we were thinking of the time-like circle. Now it's a space-like circle, but it's actually the same harmonies. So these Wilson lines get shifted by this constant. So the solutions parameterized by little w's up to this shift. So the way to parameterize them with a single value gauge invariant way is just to exponentiate. So capital W I e to the I e little w I over H. Which one's usually called the Wilson line? Is it this or is it this?
I call it the exponential. And then the Wilson line's gauge.
Yeah.
That makes more sense. Okay, so we have a set of solutions that are parameterized by the Wilson line, capital W. They're just phases. So there's two phases, so the solutions are parameterized by two circles, W1 and W2. So the space of solutions is a torus. Okay? Everybody happy with this? Now, something important. The space of solutions is a torus, but the dynamics governing these solutions is first order in time, not second order in time. So what does that mean? It means that the space of solutions, the torus, you should think of as the phase space of solutions, not the configuration space. Okay? It's the space that is telling you about momenta and position in a classical dynamics. So you've got a phase space which is a torus, and importantly, a torus has a finite volume. It's a compact matter. So what do you do when you quantize a phase space? Very roughly speaking, if you think someone in Bohr, some old German guy, Sommerfeld maybe, Bohr Sommerfeld, is that what it's called? Picture, you take your phase space and you parcel it up into little areas of order h bar, and every area of order h bar corresponds to a state in your Riemann space.
H bar by 2 times 2 pi.
Probably by 2.
It's just like, or this should be k states, right?
It's going to be M.
I think it's H bar times 2 pi.
But it shouldn't really. There's no reason that should work, right? Because that's only true in some large limit. So what's going on here is you've got a finite volume manifold, but that manifold is a phase space. But whenever you have a finite volume phase space, quantizing it gives you a finite dimensional Riemann space. Okay? It's not something we're used to thinking about when we think about taking a classical mechanics system and quantizing. Because in nearly every classical mechanics system you've thought of, you've got an infinite dimensional phase space. The harmonic oscillator. It's, momentum can be as large as you like, so it's got an infinite dimensional phase space. Please.
Sorry, I just have to take Shiraz up on this. Isn't number of states usually volume, when we do thermodynamics, is V dqp over 2 pi h bar.
Exactly.
So it's that 2 pi.
Yeah.
Okay. Yeah. Then I agree with you.
I thought you were saying the other way.
No.
Yes, then I agree.
Okay, so the key point is that finite volume phase space on quantization gives a finite dimensional Riemann space. Okay, so that's the expectation. Let's see how it actually plays out in this case. We're not going to try and do this Bohr Sommerfeld thing. We're just going to do the quantization. So the quantization you just quantize canonically the action that we just had.
But could I say, David, you get the same answer with Bohr Sommerfeld, I think, because it's also true.
I think think that's true, and in general there's a quantization requirement on the volume of any free space, and it must have that 2 pi.
Yeah, so just to say, your holonomies each of length 2 pi. So the volume of phase space is 2 pi squared. The effective h bar is 2 pi by k, or 2 pi by m.
Because there was an m in the
Because there was...
The effect is this m here.
Yeah, exactly. Your action was m by 2 pi a1 dot into. a1 dot times into. So effective h bar is 2 pi by m. And then, but you're supposed to multiply h bar by 2 pi. So 2 pi squared by m. So 4 pi, 2 pi squared by 2 pi squared.
Strictly speaking, that should only be valid in
large m. But it's
a large number of
flat.
degrees of freedom.
Yeah.
I don't know, but it also works when you have, CPN, for example.
Yeah, doesn't that k go to k plus 1 there?
There's some subtle shifts,
yes.
But up to that,
yes.
The subtle shifts are actually, it's a normal ordering ambiguity as to how you...
Yeah. But if you just get those homicides, you might be off by 1.
Yeah, maybe that.
Yeah.
Okay, so just write down canonical quantization relations from the action we started with. This tells us that the little w's obey this quantization relation, which if you use BCA, the Hausdorff formula, it's easy to convince yourself that the Wilson lines, which are the gauge invariant objects, satisfy this algebra. Okay. And this is exactly the same algebra we saw when we were talking about Loftus space. Okay. So the punchline to this argument is that you have to have this algebra acting on the space of ground states, but this algebra can't be realized with just a single ground state. The minimum number of ground states you need to realize this algebra is n. When we wrote down when we looked at the Loftus states exactly how it works. We call them T in that case. When we were thinking about anions being moved around the cycle, that's exactly what the Wilson line is doing. It's moving an anion.
And just to be a purist, sorry, but there's something fishy about this argument.
Oh, why is that?
Which is that there's no n cross m algebra that W1 commutator W2 is equal to constant.
Yes.
If you take the trace on both sides, left hand side is...
This has to be infinite dimensional operator. But it's not gauge invariant, so that must be there.
Exactly. So I'm saying it's the right answer, but the intermediate steps are a bit fishy. You can't write it in n cross n. This, yes.
That's right.
So it's, yeah.
No, I think it's probably right because this isn't acting on gauge invariant ground states. So probably this is infinite dimensional, but it's acting on sort of gauge copies of these gauge copies of the true ground states. That's probably what's going on. This is the same degeneracy.
Yeah, no, I was going to ask the same thing, but the intermediate. That is, okay, just but let me ask a more immediate question. Sorry. So, on general grounds, if the volume of phase space is finite, it's a finite division.
Yes.
Because we can just show that from some general. It must be something very dumb, like this.
You have to in general, you have to generalize the rules of quantum mechanics.
Right. That's what I
to do this quantization. This is the subject called geometric quantization.
Okay.
Yeah. Which Milton has written dreams.
And it's all about finite space.
And one way of doing it is to look at the section. You know, when you've got a complex structure, is look at the holomorphic. And there's a whole.
Okay. Alright, good.
I see. Okay, so this is the punchline. You take Chern-Simons theory at level m, put it on a torus. The number of ground states is f, because that's how many is needed to solve this algorithm. That's exactly the same as we saw for the Loftus states. We put m on a torus. Loftus states infinite fraction 1 over m on n. This is the subject of topology. Good. So everything is. Is looking good. That's the effective field theory for the Loftus states. Let me very quickly tell you how you get the effective field theory for all other states, because it's very straightforward. So this is what's called the hierarchy.
And just out of curiosity, David, this is something they have done, right? They have actually engineered systems on Tori and no, they can't do that. will not be so hard. What's a theorist to know like us?
You just got to glue it together, right? How hard can it be?
Yeah, right.
Of course, then you need a magnetic monopole to thread the magnetic field through this. That might be hard.
Did you need that for seeing these degenerating?
No, but if you think about a genuine system,
Yeah.
then you need a magnetic field.
Yeah, right.
So that might be a tricky bit. Right. So finally, I'm actually going to revert to units like E squared equals h bar equals 1. As I said, all other books did it.
It's always what I did in my mind.
It's it was actually useful. I genuinely was surprised when I saw that k wasn't an integer. K was an integer times e squared over h bar. So it's been useful, at least for me, to see how this works. All right. So if you remember, the Lofton states appear at 1/3 and 1/5 is also seen. There are then dozens of other fractions which aren't 1 over 2/5 is the most prominent in experiments, and others that I can't remember. And we have various pictures about how this emerged. So one idea of the hierarchy was that you looked at a Lofton state, you looked at the quasi-holds above a Lofton state, those quasi-holds then formed their own multi-pole state, and then more quasi-holds on top of that state formed the multi-pole. So you get this sort of leveled structure of multi-pole states. So let's just see how to describe this in this picture. The punchline is really easy. The punchline is the Lofton state will be got if we assume there was a single U1 emergent gauge, topologically agreed. Suppose you have systems with more emergent gauge fields. What would you get? Well, what you're going to get is exactly this hierarchy. So let's just see how it works. So let me just sort of summarize how we got Lofton states. So to get Lofton states, what did we do? The first thing is we write the electron currents as G nu E nu 0. Okay? And so we wrote the electron current in terms of this new emergent gauge field. And then we added a Chern-Simons term that we knew. Okay. The fact that the electron current is given by this tells us there's a mixed Chern-Simons term, capital A mixing with little a. And then this determined the level of the Lofton state. Then easy. So to get the hierarchy states, we just repeat it. So what do we know? We know what the quasi-holds are. The quasi-holds are the objects which couple to little a. So there's a current, J, which couples to little a. So we write the quasi-hold current as J little j nu is 1 over 2 pi epsilon mu rho d mu a tilde rho, where A tilde is a new second emergent gauge. And little j is by definition the thing that couples to little a. And then we add a Chern-Simons term. So what does this mean? So the effective action is going to be an effective action of little a tilde little a and capital A. Two emergent guys that are background gauge field. So what do we have? The first term is the term we had before. We know that capital A has to current coupled to its current.
I forgot the slogan, this Gen slogan. Was the Gen slogan that the new states are the quantum Hall effect for the quasi-particles of the old state?
No, that was sort of the earlier Halperin approach to this. So there were two approaches to this hierarchy. One was Haldane and Halperin saying exactly what you said. Jane's slogan was more to do with attaching fluxes in various ways and then putting those composite objects into their own Hall states.
So the Hall state of what? Of the electrons of the quasi-particle, or just something?
You take the composite, what's called a composite fermion, that was the electron plus fluxes, and you put that composite fermion into, into say the second. It was more complicated, right? You put it into a second Landau level, and you have to project down. This seems much more.
I was just trying to translate that. How is this the same as that?
This is not obviously the same as that. This seems much more along the lines of the Haldane Halperin.
Yes. So you're just doing the quasi-particle. Yeah.
So there's been a big controversy in the literature about whether these two approaches, the quasi-Halls forming their own Hall state versus the Jane composite fermion approach, whether they're the same or not. They give the same answers for filling fractions. And Jane, has many papers arguing very strongly that they're totally different. But I think they're not. I think they're probably different ways of seeing the same thing, because they give the same answers. But the connection between them is not so obvious.
But mu is equal to half was also explained in the Haldane approach?
No. No, that was really the shining glory of the composite fermion. You can explain it using these Chern-Simons theories, although you can explain it using the dodgy Chern-Simons theory that I wrote down. Where the Hall conductivity wasn't quantized, 1 over M Chern-Simons. So that's what's called the HR, Halperin Lee. There's only 5 people. Keep reading. There's something called the Reed-Retzai wave function, which is very important, and there's something called the Retzai-Reed wave function, which is also very important.
I shouldn't think of a condensed matter physicist reviewing string theory. There's only really one person.
Okay, so a background gauge field comes to current, and then you add a Chern-Simons term for that new background gauge field. And then new emerging gauge field forms the new current which couples to the old emerging gauge field. And then you add a Chern-Simons term for the new emerging gauge field. Okay. So 4 terms. These two are fixed just by the fact that currents are written in terms of emerging gauge fields. You get 2 integers to play with. If you now integrate out little a and capital A in the same way we did before, you'll get an expression for, integrate out little a and little a tilde. You'll get a Chern-Simons term just for capital A with an expression here. It's an illegal expression because we didn't account for fluxes, but you can trust it for any fraction. And you'll find that the filling fraction is 1 over m minus 1 over m. So it's this continued fraction.
The minus is because you put the minus.
Yeah, well, it's definitely because I put the minus down. I'm worried that it's wrong. I think I was careful in checking this one.
That looks right.
Okay, I think it's right. And obviously you could keep going, right? You could add a third emerging gauge field, which couples to the current, which is third emerging gauge field, which is related to the current that couples to little a tilde. And if you keep going, you get these continued fractions that appear here, which was exactly the same thing that we saw in the...
This minus is somehow because one is a particle, the other is a whole. Is that... It really is a reflection of the second, the minus of the second line.
Surely, yeah, it must be...
No, not... I think the 4th line wouldn't have changed the sign.
Yeah,
because you square it and you will...
until it goes to minus.
No, you're right. But would have. Both those I put. So if you change either of those minuses, you would have. Okay.
Why doesn't the second emergent gauge field not couple the background field?
Oh, by definition, the background field couples to the current, and I defined the current to be epsilon d little bit. But I think what you're saying is that this isn't the most general Chern-Simons theorem that I can write down. So the most general thing I can write down is what's called a K matrix, and you have n Chern-Simons. Here it is. So there's an n by n matrix. Okay. And then you can decide which combination of these you want to think of as the electric current. So we have Ti, epsilon u rho,
But just ask Mankesh's question again, why are the holes and electrons? Sorry, just say again what the physical interpretation of the data. You were saying something about holes, and that's what it is. The quasi-holes.
Are we worried about the minus sign or just
No, just the fact that the quasi-holes and the quasi-particles are playing such an asymmetrical role.
No, I don't think they are.
I thought the quasi-particles are...
M going to minus M, M tilde going to minus M tilde. Well, one of those will be the quasi-holes forming their own quantum Hall field, and the other one will be the quasi-particles forming their own.
Is it still true that the particles that are charged under little a are the quasi-particles?
Yes.
And the quasi-particles that are charged under little a tilde are the quasi-holes?
It says no.
No. Okay.
No. The particles that are charged under little a are quasi-particles and quasi-holes, depending on whether they have a plus or minus.
So then, say again, what is this little a tilde?
So little a tilde. So J nu is electric current.
Can I venture a comment? Sorry.
Yeah.
The little a tilde is the topological field for the quasi-particle problems. It's the extra. It's what you were saying. I mean, it's the Hall effect for the
quasi-particles. Yeah.
So depending on whether this is positive or negative, it's either the particles or the holes which.
Why?
If you remember when we had this plateaus. Okay, so this is a third, and if the holes condense, meaning condense means form their own state, you go up here, and if the particles condense, you go down. By the way, it's just occurred to me that this flipping of minus signs we've seen before. To get nu equals k, where this is defined now by the Hall conductivity, we needed a positive k Chern-Simons of this. Then to get nu equals 1 over m, we needed a minus sign here. And now I've chosen a plus sign there and then a plus sign there. So there does seem to be this flipping of signs as you go from one level to.
And you can continue the sequence forever.
You can continue
And
forever
this is
and
the
you
game.
can continue fractions.
Yeah.
And they're seen experimentally here. It's all about the 6th level. It's pretty impressive. But by the way, since you asked about this K matrix, let me tell you, there's some lovely formulas. So if you this is the most general thing you could write down. It's certainly not true that for all Ks you could find an experimental realization. But it is true that there are more Ks of interest than just the ones that appear here. So one example is you may have multi-layered systems, and electrons can jump between layers. Then you get some choice of K that I've not discussed. But there's some lovely formulae. If you just write down this is the most general thing, then sigma xy is quantized. And this is its value. Meanwhile, there are a whole bunch of quasi-holes, one for each gauge field, and their charge is this, and the statistics between different polygons. So alpha is the statistical parameter that I mentioned. It's 1 over m for Lockwood space. But the statistical parameter between different objects is just this inverse. So there's this lovely formula that you can derive very easily just from this general approach.
Sorry, I have one more question. In the filling fraction formula, the f tilde we earlier got it as an even integer, right?
So this is again.
Last time when we worked out the filling fraction for this hierarchical problem, we got it as 1 upon m plus 1 upon 2p.
Oh, right. That's
it was an even.
That's right. So that's because you know the even or oddness of this m is due to whether we have bosonic or fermionic objects. The same, I think, is true of this. When we did that, I think we'd chosen this to be odd.
Yeah,
and then this had to be even. But yet, none of this is fixed into this. So, yeah, I think here we're getting a more general class of systems than you would in a specific example. By the way, there's one last nice formula which I'll add to this. It's the topological degeneracy. So on a genus G surface, this one's harder. The degeneracy, the delta K to the G. It's quite a pretty form.
So sorry, you said it just now, but so just even without the n tilde, as a set of Chern-Simons theories, of course, we could have had n to be even as well.
That's right.
But then when you work out the statistics of the quasi-particles, they would have been bosonic.
Not the quasi-particles, the underlying objects.
The underlying, which couple
The electrons themselves.
Oh, the underlying electrons themselves. The electrons themselves, okay.
Which is fine.
No, it is fine, but probably we don't want for real experiments.
No, but I wouldn't be surprised if there are experiments. That's right. I don't know what they are. But you want to cold atom, blah, blah, blah. Anything you could kind of imagine in comparison. It's probably right.
So then you say you'll have the fractional with even denominators.
Okay, so this is actually the most general class of abelian quantum Hall state, where abelian means that the statistics are just phases rather than something more interesting, like we saw from the more read state. You could also ask, how do you get more abelian quantum Hall state? How do you get more read state, for example? And the answer is dead simple. The answer is we need an emergent non-abelian gauge field. So if you write down non-abelian Chern-Simons theories, they're the effective theories for these non-abelian Hall states. So we talked about more read. More read, it turns out, is SU2 Chern-Simons at level 2. That'll give you in Wilson lines, you compute the degeneracy of the Hilbert space with Wilson lines. That's exactly the degeneracy of these quasi-holes that we saw before. The braiding of Wilson lines is related to Wisson's work on Knox polynomials. It's precisely the braiding that we derived from Myron zeros. So there's this lovely connection between non-abelian Chern-Simons theories and a whole rich story there. The stuff we saw before. Some of which are discussed in the notes if you're interested. It's a vast subject. I've only sort of spelled out what I think are the main results with no derivations. So, I was going to do a bit here, but I think given the time, we'll just questions.
Yeah. And then, I was going to ask this. Is it tempting to say that, going back to the Shiraz was trying to ask, if you do transitions between atoms, when you get extra propagating degrees, isn't it tempting to say that it's charge matter that comes to these Chern-Simons theories? Or is that? I mean, I'm just wondering, you have this Chern-Simons theory as the low energy effective theory, and then you know that extra light degrees are generated when you go from one pleasure to another. So could it just be that you, again, the underlying reason for this, that these are the most relevant terms and so on, is true, but now you get something a little, something more, and you know you're getting a longitudinal conductivity, so you have some charged matter, so you just put in.
And we know that the quasi-holes are charged under the emergent rays, like quasi-particles.
But you really want to talk about the transition between photons. There's some critical point there.
Right,
and
right.
If you think of that critical point as moving from one of these effective theories to
I mean, if you just add fermionic matter, you do have a critical theory without any mass to Chern-Simons theory.
you want to add fermionic matter, put on a chemical potential, so it forms a Fermi C, and then add the Chern-Simons. Is that the critical theory you have in mind? At the Dirac.
Yeah, I was just thinking at the Dirac point, because you just aren't
relativistic.
Relativistic. As an example of the critical theory.
Yeah, although the quasi-holes don't have relativistic dispersion.
So then I would rethink conformal, wouldn't we be scared? I don't know.
I don't know is the answer. I mean, our whole starting point was assuming there's a gap.
Yeah.
And now you sort of want to push it to where the gap closes and hope you can add in the extra degrees of freedom to capture that. If you add in the right one, surely, it's not clear to me that Chern-Simons terms are the dominant player. Okay. I don't know if anyone's made improvements.
And what is the description of the nu equals half state? This is what you were saying, it's more equal.
Oh, sorry, so there's not
Nu equals half state.
There's two nu equals half states. There's the Fermi surface, and there's the Moore-Reed. You mean Moore-Reed?
I suppose I do.
Why isn't that 5 halves?
It's 5 halves. It's 5 halves, but you kind of strip away the two.
Okay.
Yeah. Okay, so Moore-Reed.
Simple nu equals half doesn't require any Chern-Simons, it's just free particles.
Do you know it's not? No, this is the debate that's happening at the moment. The old HLR theory was 3 fermions piling up to a Fermi surface, coupled to a Chern-Simons term at level 1/2. And if you look at a Fermi surface coupled to a Chern-Simons term, you still have massless Fermi surface-like properties, but it's a non-Fermi liquid, and one which I want to look at. I think it's the simplest example of a non-Fermi liquid where everything's under control. The more recent conjecture of Son is that actually there's no Chern-Simons. I don't think we. Okay, so Moore-Reed, which is nu equals a half.
Yeah, sorry, can I just ask something then? So, again, with M odd, with M even, there's no issue with the statistics. We are going to talk about that. Is it? Then the basic electrons would have to.
So if you remember, Moore-Reed is a lovely wave function. The M, which has filling fraction 1 over M. But because of this fat field, when M is 2, this is nu equals a half, but for electrons, not bosons. So this is Moore-Reed as opposed to Lofton, which is, of course, a bosonic.
Would you have to really calculate these statistics, or am I mixing things up?
So we calculated, you mean in the Chern-Simons?
Yeah.
We calculated statistics of quasi-holes, the quasi-particles, rather than the underlying electrons.
So then M, so you're saying, okay, as long as the quasi-holes or particles are bosonic or fermionic, even if the underlying electrons were fermions, that's okay. There's no issue.
But for the effective theory of this state does not fall into this class. So it's not, so as I'll explain, it's not a union Chern-Simons. So for Moore-Reed, which is this theory here, that's there's some issues. Like, in general, you can have this for general M, but the story of quasi-particles is always the same. There's some things I don't understand. I suspect it's because they're not understood. I've certainly tried to find an again, it may just be my evidence. So m equals 1 is a bosonic Moore-Reed state, but still has the same properties. It's known that this is SU2 level 2. So what do I mean by that? SU2 at level 2 has a number of Wilson lines. You can write that. Sorry, there's going to be a lot of. I'm not going to explain everything, I'm afraid. But ask me if you want me. If you want me. The Wilson lines in this theory are spin 0, 1/2, 1. It turns out if you try to put an object of spin higher than, so spin means the charge of the representation of the SU2 gauge. If you try to put an object with, say, spin 3/2 or higher, the flux sort of screens it and hides it. Flux for this. The height of representation you can go is related to the level. So it turns out you can only have these. These, of course, have dimensions 1, 2, 3. And then what happens is there are these, the tensor product, the usual Clebsch-Gordon coefficients that you get between SU2 representation are changed in Chern-Simons fields. You only get a subset of things on the left-hand side. So 2 times 2 is 1 plus 3. This one's unchanged. 2 times 3 is just 2. Okay, this is a half times a 1, so you expect this to go a half, 3 halves, but you can't have 3 halves because it gets screwed, so you just have this. And then the surprising one is 3 times 3 is just 1. That's surprising because spin 1 times spin 1, you would expect to go 0, 1, 2. 2 is not allowed, but you might think 1's allowed, but it turns out it's 1 being 3. It turns out it's not. So then, if you put in n Wilson lines in the fundamental 2, then the number of singlets on the right-hand side. See, so this is 2 tensor 2 tensor 2 tensor 2. String them all together. On the right-hand side, you'll get a whole bunch of stuff usually, but now the only stuff you're going to get is a singlet, spin 1/2 and spin 1, with some degeneracies. And the number of singlets that you get is equal to 2 to the n over 2 minus 1. That's exactly the same counting we saw for the number of states, quasi-holes in the Moore-Reed state. Number of quasi-hole states. So that's the math. These are the Moore-Reed methods. Sorry, that was probably completely unintelligent. I apologize. By the way, there's one thing to say. It's related to this. So what's the effective theory you would write down? So it's obvious that the effective theory is the 3x 1 over 4 pi. There's some m, which I've said is equal to 2 for Moore-Reed. S Chern-Simons, where this is the non-abelian Chern-Simons action, which we'll put down. But the effective theory has also got to tell us how these things couple to capital A. How can you possibly couple to capital A? Because there's no mixed Chern-Simons term between, I can't write A, mu, d mu, A mu, because now this is not abelian and it's not gauge invariant. And I can't write, this is gauge invariant, but this is SU2, so this just vanishes. So there's no way I can couple electromagnetism to this. So what can I do? Well, I think the answer to this was only figured out last month. It's in Appendix C of this paper by Simon. And I've been puzzled about this for ages. There's papers in the 90s by Fradkin and Wilczek that just have all sorts of stuff that just make no sense. Maybe they're right, but I can understand. Simon and Wittens explain that it's quite complicated, but they show how they say how to do it. So they say that what you do is you add new U1 there's two emerging gauge fields. This U1 maybe has something of its own. And then the key, so at the moment, this U1 doesn't know about this SU2. And so somehow we've got to know make this U1 know about this SU2, but that also seems like we have the same problems. There's no mixed Chern-Simons. So they claim there's a quotient construction. So I don't know how to write down an effective action for this, but they claim there's some where the quotient is by some discrete where you identify Wilson lines in this and Wilson lines in this, and insist that the only physical things have trivial holonomy with those Wilson lines. And when you do that, they claim you get the right effective discrete. So I haven't managed to go through it yet to really understand the details of this.
So really subtle.
Yeah.
I could never have figured something.
I also never would have thought. There's a hint. The hint is that the more read states are the first of an important sequence of non-abelian states. The sequence is called the read-Retz-IE states. And the read-Retz-IE states are associated to parafermion conformal field theories. And parafermion conformal field theories
I was wondering whether
are these quotients, and when k is equal to 2, this is the same thing as the Ising. And that's the same thing as Morley.
Morley is the same as Ising.
Morley is Ising model now. Yeah. That's how they got that actually. They just wrote down correlation function of the Ising model. So it was known from the CFT perspective that there's some quotient. So I had no idea how to do this in Chern-Simons. Actually, apparently it's in a paper by Moore and Seibach and Anderson from like the early 2000s. Some string theory, background flux, K theory, blah blah blah. But at least this quotient construction, we realize this is. So Appendix C of that paper is lovely. It's 10 pages. It's really doing all details of Chern-Simons normalizations and how you do quotients. Any questions?
So wait, is it possible to have like a sequence of non-abelian theorems?
Oh, so hierarchy.
Yeah.
What is that?
Meaning the thing that it looks tough because it's hard to couple one non-abelian theory with another.
Yeah, so whether you can do these quotients for two non-abelian theories.
Yeah.
I don't know.
Yes, the answer is yes, because you have cosec models. Sorry, G
G
mod H. H need not be abelian, neither may be G. It's not the
I think it's unknown what happens if the quasi-holes in the Moore read state themselves form a quantum quarter. I think that's not understood. I've certainly read that question expressed in several papers. We have a method using our matrix models to get hierarchies of non-abelian states. I'm not sure if there's something that we contact yet. Condensed matter paper. That's the next class. Okay, so I should say that you're not around next week.
I'm not around.
Should I just go to them?
Well, and then you're not around the week after next, right?
No, then I'm back for a week.
Well, I mean, it's up to you. I mean, if it's impractical, you should.
So we've got either 1 or 2 lectures left, and it sort of gets to the punchline is what I wanted to get to. So what we're going to do next is look at edge states. It sounds like a very strange, esoteric thing to talk about. It turns out everything is hidden in the edge states. It's something a little bit like holography, gauge gravity, duality. It's not quite as rich as that, but I think it's almost as surprising as that. So the edge states are described by some 1 + 1 dimensional conformal field theory. And the edge states, roughly speaking, know everything that's going on in the world. So we're going to show how we're going to derive what the edge states are, just for Laughlin. It's very straightforward. We're going to derive it in 2 different ways. And then we're going to understand that theory a little better. It's something called a chiral boson in 1 + 1 dimension, compact chiral boson. And it's a free theory, so we'll compute some correlation functions in this theory. And we'll see how we can recapture exactly the Laughlin wave function from the edge in a way that just appears miraculous. So that's sort of the last thing to do.
Will you be around all of 3 weeks from now?
I get back on the Monday, so around 4.
If you would have the time, I would.
Let's just do it.
But sorry, can I get what dates are?
I come back on the 28th, which is my birthday on the Monday, and then I'm around 29th. So, first.
No, okay. Anyway, I'm gone for that period.
Oh no, let's just do it next week.
No, that's okay.
No, I think do it next week.
Oh, yeah.
But next week I'm gone on Tuesday.
Oh, that is 2 weeks from now.
I'm there except for Tuesday, but Tuesday.
Oh, yeah.
Oh, I see.
But just do Tuesday.
Does anybody else have a preference? Okay, maybe I'll do it.